Thank you very much. So my name is Henryk Fiedorowicz. In this last lecture, I'm going to talk about laser plasma sources of EUV for application in nanotechnology and biomedical engineering. Before I start my talk, I would like to say a few words about the institution I came from. So I represent the Institute of Optoelectronics, which is an interdisciplinary academic research institute, MUT. Interdisciplinary is quite important name because usually the faculty we have institute, but in this institute we have a physicist or chemist depending on the faculty. In our institute there are a variety of specialists from physics, chemistry, biology, engineering. So that's why we are able to do interdisciplinary research project. And our mission is to support research and education in optoelectronics and lasers. This research are integrated with the education mission, and the permanent staff is about 170, 80 people. And there are 4 sections and 16 research groups. Majority of groups are related to laser technology, laser development, and different applications. And our laser metal interaction group is here. There are 4 laboratories: laboratory on high intensity laser metal interaction, laboratory on high energy laser metal interaction, laboratory on micro and nano processing materials, and the laboratory on nano imaging. So then later on I will describe these labs in details. I'm very glad to present this article from the August issue of Photonic Spectra. So you can find 2 partners. There is a list of photonic institutions, and there are 2 members of EXTATIC consortium, Fraunhofer Institute for Laser Technology with extreme ultraviolet technology, and our institute with laser metal interaction. So I think it's a good recommendation for all of you. This is an outline of my talk, which will be different to previous lectures because it is a pure engineering, no formulas. So I know that students usually like very much formulas, so there is no. After a short introduction, I will introduce laser plasma UV source that was developed in our laboratory. I will be not talking about different sources that have been developed in other laboratories. I will just mention about it. Our source is based on a gas path target, which will be introduced in details. And finally, I will present different applications of the source, but with special attention to processing material because of the topic of the study of INA. So, extreme ultraviolet. If we talk about EUV, so we should remember that there is a formal standard which was proposed by some time ago by astrophysics. And so according to the standard, international standard, the extreme ultraviolet is defined as a wavelength from 10 to 101 nanometer. But we know also this very well-known picture from the book of David Atwood. And why I asked David, why you put this this band here? So he told me, oh, because this picture was made by Linda, his wife. So everything was made by Linda. Anyway, you can also find this term XUV. It was used by Larissa, by Bill. So some people following French, because French people were first, they used this XUV. Extreme ultraviolet was used much earlier. Actually, it was used in 50s, in 60s by astrophysics. And then it was adopted by industry. So now everybody uses extreme ultraviolet because it was decided by industry. What is the motivation of using EUV for nanotechnology, I would say? So one motivation, nanometer resolution, which can be used in nanolithography, nanometering, was mentioned by a few speakers. But I would like to point your attention to another characteristic feature, that is penetration depth. EUV light, it is a penetrating radiation. It's penetrating through every material. However, the penetration depth is very, very low. EUV light at 10 nanometer, for instance, is absorbed in a very thin layer of different materials, depending on the atomic number, on density. For instance, polymers, it is less than 100 nanometer. For metal, it is less than 10 nanometers. So anyway, we should remember that this penetration depth of EUV is very, very low, that can be used in different applications. It's a very important parameter. Generation, of course, the best sources are synchrotrons, free electron lasers, but we are talking about another alternative sources, plasma sources like discharge plasma. So I will be talking about laser plasma. Laser-produced plasma. So after this lecture given by Jerzy Wimbuch, I should skip. But I would like to say a few words which is important from the point of view of generation of X-ray in UV. So laser plasma is produced when we focus high power laser beam, laser pulse on the surface of the target, solid target or any kind. And the intensity or power density should be 10 to 11. So in this case, we have EUV radiation, because the temperature in this case reaches numbers, a few tens of electron volts. If we have 10 to 13, 10 to 14, so the temperature is much higher. It's approaching a few tens, a few hundreds of EV. So in this case, it is a good source of X-rays. Where the X-rays or EUV comes from the area where is the highest temperature, highest density, because it means that in this region the coupling and absorption of laser energy is the highest. So this is a region nearby, so-called critical density. Critical density is a density of plasma, which is characteristic for the wavelengths of laser radiation. For 1 nanometer radiation, it corresponds to 10 to 21. For 10 nanometer CO2 laser, it corresponds to 10 to 19. Okay? And there is another characteristic surface, so-called ablation surface. It is a surface from which material is flowing out from the surface. Inside the target, there is also a shock wave which is propagating inside material. So the laser plasma EUV source schematically is a very simple device. It reminds X-ray or EUV tube, but instead of E-beam, we have a laser beam, unfortunately. Laser beam which is focused onto the target. And in the results of interaction, we have a laser-produced plasma. We know from different presentations, from different simulations, that the optimum parameters of the laser plasma for EUV source should be like this: about 40 electron volts and density 10 to 19. This is very important information, because you know that I already said that the maximum production is in area where is the critical density. Critical density for CO2 is just 10 to 19. So it means that the optimum laser system for EUV laser plasma source should be CO2 laser. That was finally recognized by industry, and now you see that main suppliers of laser-produced laser plasma UV source for lithography, they consider to use CO2 laser. Laser plasma UV source has some characteristic feature: high single pulse brightness, short pulse duration, easy tuning of wavelength by changing the parameters of laser pulse and by changing the material of the target. And also low investment cost. If you compare the cost of this source, which is on the level less than, I would say, starting from 50,000 euro up, but it is a few orders of magnitude less than the synchrotron, for instance. However, this source has two at least two main disadvantages. The first one, it's a target operation. For single shot, we can put any plate or whatever. But if we work with operation, we have to use some rotating disc, rotating rod, wire. So you can find tens of solutions of this problem. Sometimes very, very complicated, really. Another problem is the target debris production. Because of ablation, during of interaction of laser paths with solid material, we produce a lot of products. It's debris is composed from neutrals, from ions, from particles, and so on. So actually, this is a very good sputtering machine, and it is used for pulse laser deposition. But when you use for as a source, it's very detrimental and very, very bad. So we have to solve this. Again, you can find more than 20 publication papers, PhD theses, how to reduce, how to mitigate the debris production. We came to the conclusion that, okay, why to solve the problem totally and to eliminate debris. So we have proposed such a, we call this gas path target. And we are using, instead of a solid material, we are using gas, which is injected to the area of the focus with the proper density to have a good coupling of laser energy and to be able to produce high density plasma close to critical. And also the size of this should be comparable with the size of the focus. So it is created by injection of the gas under high pressure through the nozzle with the diameter about 0.5 millimeter. It can be smaller, but in this case, because of viscosity, we are not able to produce high density. So this is a compromise. But anyway, we demonstrated that we can produce a critical density plasma using such a device, such arrangement. We have in our laboratory, we have developed different types of electromagnetic valves to form a gas path target. It's one of example. Arrangement is really very simple. It says gas reservoir. Can we change the battery? Because I think that there is. No? It's a gas reservoir. We fill with gas up to pressure about 10 bar, but we also made up to 100 bars. And this diaphragm, which is open, which is driven by the coil and the nozzle in the 4 minutes. It's very important issue is to characterize the gas path target, because when we use a solid material, so we know where is the boundary, what is the density, and so on. But in this case, there is some area which density profiles and so on. So there are some methods. You can use interferometry, refractometry, but we are using X-ray radiography with the laser plasma X-ray source, which illuminate and the target which is under study, and on the CCD camera we obtain such a shadow and after processing we can obtain the gas density contours, gas density profile. So you see that it's not like a real jet, it's like a ball. So that's why we prefer to call this gas path target. Anyway, we can see that we can reach very high density, but very close to the nozzle. Density 10 to milligram per cubic centimeter corresponds to the density, to the pressure about 3 bars. So in this region, we can produce a critical density of the plasma. This target approach was introduced by us almost 20 years ago, very old issue. At that time, the motivation was elimination of debris, operation with repetition, and also improvement of efficiency. At that time, we were interested in X-ray generation because there was no discussion about EUV. EUV was at that time didn't exist, And when I presented this target at the conference in San Diego, so I was really surprised, because after my talk I was surrounded with people attending this meeting, and everything asked me about details, because they didn't believe that we are able to produce high output of X-rays. And after my return to Poland, I got emails from Livermore Laboratory, from ATT Bell Lab, from IBM, and they wanted to come, and they came with their own detectors, and we performed experiment. They checked, they find it's okay. Finally, they accepted these results. They invited us to Livermore, and we repeated again experiment. So anyway, there was strong interest. And also, we were starting development of such a device for the laser plasma that was used at ATT Bell Lab for X-ray proximity printing lithography. But when this device was ready, I got information that the program of X-ray lithography was cancelled, was stopped. So then we had to start interest to EUV. This target was used in different experiments in different laboratories, including X-ray lasers. I would like to show my favorite. In collaboration with our Russian colleagues from Moscow and from Livermore, we performed some few experiments on high resolution X-ray spectroscopy. And our colleagues, they found this plasma created with the gas path target is ideal for X-ray spectroscopy. Why? Because when you have a laser plasma from the solid material, so the plasma is expanding with a high velocity, sound velocity. But when you have a plasma which is produced with gas path target, which is more or less stable, okay, and there is no broadening because of Doppler effect. So we are able to measure the lines which were not visible using laser plasma from the solid material and from other plasma. Like, for instance, this is an example of the spectrum for argon plasma obtained with our very simple arrangement. At the same time, from the tokamak, they measured the same spectra, but you see that the resolution, even this was made using very sophisticated spectroscopy stuff, was worse than in our case. This is another example, plasma channel formation, depending on the distance from the nozzle output, close to the nozzle, where the density is very high, and we observe the critical density. We observe the self-focusing of laser light. And because of self-focusing, the intensity was much higher than it was possible to obtain without the self-focusing. And so we observed very high temperature approaching 700 EV. This was confirmed in computer simulation done by colleagues from Chelyabinsk laboratory, Igor Głazirin. He made such a simulation, and also he showed that in such a high density plasma, we observe self-focusing of laser pulse. This is another experiment performed in collaboration with our colleagues from Germany and from Jerusalem. We measure very spectra from xenon with very high spectral resolution. This was done in water window. We measured for the first time very good spectra from nitrogen. We also perform experiment at Osaka University using this experimental setup. So you see different EUV and soft X-ray grazing is a spectrometer. So we obtain spectra, EUV spectra for different gases, soft X-ray spectra. This was used for soft X-ray contact microscopy. Professor Shinohara and Kinjo-san, they study chromosomes, and they got such images. They were very excited with this, even that it was published, but I don't know what is published here because everything is in Japanese. However, during this research, we found that this simple arrangement, I mean gas path target, is good, but not so good. It's good for single shot, for short operation time. After some time, because in this experiment we could work with repetition rate up to 10 Hertz. So after some time, we observe a degradation of the nozzle because of the direction of the plasma. When the plasma was put close to the nozzle output, so after some time, let's say half an hour, there was a decrease of EUV output because of nozzle degradation. There was also self-absorption of EUV radiation in a cold gas surrounding the hot plasma. It was especially bad in the case of xenon, where this you see there is a EUV transmission in xenon, and here, where is the most important spectrum from xenon, this transmission is very high. It is very low. So we propose some improvement, and we have developed a so-called double stream gas path target. In this case, the working gas is injected not in the vacuum, but in the additional stream of gas which is surrounding this central stream of working gas. So this working gas is coming through the nozzle in the form of the orifice, and this outer stream of low Z gas, helium or hydrogen, is flowing through the nozzle, which is in the form of the ring surrounding this one. So the electromagnetic valve system is presented here. There are two valves placed in the common body, and these two valves supply such a double nozzle arrangement. And the difference you can see here. This is an ordinary gas path target. You can see that it spreads for all space. And this is this double stream gas path target. Now we are able to produce a high density target at the distance even 2 millimeters from the nozzle. So now we are able to produce a hot plasma which is not at some distance from the nozzle, no nozzle degradation, no problem at all. And this new arrangement was studied at our institute using neodymium glass laser system. We measured spectra in EUV range. We found that there are some room for optimization. The first experiment on EUV emission actually was performed in the Netherlands. So you can see the result. This is the emission EUV production from the ordinary gas path target with xenon here. And this is for double stream gas, so almost 20 times increase of the production. And again, EUV emission, detailed emission studies, EUV emission studies we perform at Osaka, and we use this Hitachi grating spectrometer, and you can see this blue line. It is an ordinary gas path target, and the red one more than 10 times increase of the efficiency when we used double stream gas path target. This is a summary of this measurement. So you can see the emission from the xenon target, double stream gas path target, and in the same place we put the solid target. So you can see that this is for aluminium. This is for iron, for copper, and for tin. Tin, of course, it's the best radiator, but you see that the problem is really serious. Anyway, you can see that using this target, this gas path target approach, we are able to produce higher output than from the solid target. With this new results, we proposed, because at the time the MEDEA Plus program related to EUV lithography was established, and under this program we proposed to develop laser plasma UV source, low average power, but which would be dedicated for metrology application. Because in this consortium, everybody said that there is a strong need to have such a laboratory source of EUV. So we said, okay, we will do this. And we made such a laboratory model of this source, which is presented here, a very small arrangement. We used a commercially available neodymium yak laser produced by a Lithuanian Expla company, small chamber and diagnostic instruments. We measured, these are EUV source characterization measurements. We measured spectrum. We found that conversion efficiency in band at 13.5 is about 1.5%. We measure this with three different methods, with the different detectors, calibrated photodiodes and calibrated CCD cameras. This is a spectral image showing that the size is approximately 400 micrometers. Time duration is slightly longer than the time duration of the laser pulse. And the conversion efficiency, 1.5%, is a quite good result, because the best results for solid xenon was not higher than 1%, right? Something like 0.8 up to 1. This is, however, this is not in 2% bandwidth. It's slightly larger. So, but anyway, this is quite good result. And finally, we have built a compact laser plasma source like a EUV lamp. So you have Aachen EUV lamp, we have Warsaw EUV lamp, which is presented here. So the idea was to have such a very small device that will be fitted to some experimental chamber, which is used for some metrology application, for characterization of the mirrors inside, or maybe resist or whatever. However, the interest of these companies and institutions involved in EUV lithography business was finally not very much. They were not very interested in using of our source. But it was used by Rafał Rakowski, who stayed in UCD for some time. In his PhD thesis, he used this source for characterization of polysilicon multilayer mirrors and to study degradation of polysilicon mirrors, which is very crucial task, and found that this source can be useful. At that time, we also were involved in larger experiments using pulse, Prague Asterix laser system. And under this laser Lapierov access program, we propose to combine our target with this large laser facility to produce as much as possible X-ray and EUV photons. So we built a system to produce such a large target. And this is a schematic of this experiment. Here you can see this chamber, target, transmission spectrometer, silicon photodiode, and to measure X-ray spectra, we used in collaboration again colleagues Thomas Wilhelm from Technikhochschule in Remagen. They have very nice spectrometer, and we measured spectra with high resolution. So this is example of a nitrogen spectra. We measure output, you see, 5, 10 to 15 photons in a single line. So from simple calculation, we know that for a single shot exposure, we need 10 to 15 photons in band. So we see that using this source, this was discussed, but anyway, Thomas said that it would be possible to get a single shot image for the first time, not for a few seconds exposition when it is how it is done at synchrotron. We also tried xenon, and for xenon we measured a huge amount of we were surprised that the conversion efficiency was so high, that almost 60% of laser radiation was converted to short wavelength radiation in different energy bands. And so this source was it was originally proposed by Libor Jucha, that okay, why not try to use this source for direct photo etching? And they tried earlier to direct photo etching using a solid target, but because of debris, this sample has to be placed far away from the plasma, so the effect was not so good. But in our case, we could put the sample close to the plasma at the distance 3 centimeters, and after even one shot, we observed direct photoetching of polymers. This is an example here. This is for three shots of Teflon, and when I presented these results in Japan at the conference on processing materials, so people who are dealing with etching with plasma, so they didn't believe that that such a deep etching deep hole was obtained in a single shot. So this is for for us, for non-specialists, this result is not so important, but for specialists, it's the processing polymers with EUV light is not a new topic. It was made for the first time in Japan in '95. They demonstrated the direct photoetching using synchrotron radiation, using such a compact, small synchrotron. And they demonstrated for the first time non-thermal ablation of Teflon with the ablation depth 200 micrometers, aspect ratio. This technique, because you know that any synchrotron you have a dedicated beamline, sometimes few beamlines dedicated to micro machining, microfabrication, to LIGA processes. However, LIGA process requires high energy photons, so it means it requires large synchrotron. This is also not a dry process. Now, any process which is dry, which is preferable, because in this case, we avoid sometimes very, I would say, dangerous chemicals. And also, for this technique, I mean EUV processing, we don't need high contrast mask, which is needed for LIGA process.
What do you mean with this mask? What is it?
Sorry?
This mask, what it is?
For LIGA, is needed mask. Okay, but when you use high energy photon, this mask has to be rigid. Okay. For this technique, the mask is very thin. Its production of this mask is much more simpler than for LIGA. Producing mask for LIGA for high energy photons for deep etching, for deep X-ray lithography is problem. It's a problem, as I know. I was told about. This is another example of processing polymers with synchrotron, again in Japan, but in this case they obtain higher aspect ratio up to 15, and they use 10 nanometer wavelengths, and they produce such submicron structures. Also, some research has been done in the United States at Louisiana State University. They use higher energy photons. I would like to point your attention to this number, 40 micrometer per hour. 1 hour exposition time was needed to produce such, so it is not very, I would say, exciting result, but anyway, such a structure could be reproduced. EUV processing was also obtained at the free electron laser. This is example of flash. They observed some leaps structures. It was done by Libor. This is a example of nano-patterning processing using EUV laser done by Przemek Wachulak during his PhD. He used this small discharge, capillary discharge EUV laser, and was able to produce very nice nanostructures down to 58 nanometers. Another group is doing research at Göttingen. It's a group headed by Klaus Mann, and they are using laser plasma source with hourglass path target. Sometimes they are using also a gold to have a smaller size of the high brightness. And the source is combined with the Schwarzschild objective, so they can produce such a structure with very high high resolution. They also can use this for another purposes. Anyway, they do this similar research. And the third group, because the problem is that there are only 3 groups working on EUV processing material. This group in Japan, group in Germany, group in Japan in Tsukuba, headed by Makimura-san. So they have a laser plasma source with a solid target. They are using such an ellipsoidal mirror for the focusing of X-rays, or EUV rather, because it is around 10 nanometer. So they produce such nanostructures at silica, but also now they are using this technology for processing polymers. And the third group, it is our group. So the question is why only 3 groups are working in this topic. It is so new, or it is so useless. So I don't know. Maybe after in your study we will see. And so this is our arrangement, also quite compact. So you can recognize this compact EUV source, which was developed for metrology application, but because of no interest, now we are using for processing materials. And inside this chamber, we put ellipsoidal EUV collector, which is, I would say, the most important part of the system, because it allows to focus, to collect radiation from the point-like source, and to focus onto the focal plane in which we put the irradiated sample. And these are parameters of this arrangement. So this is a spectrum, dominating feature at about 10 nanometer, because we are using a xenon with krypton. Because of this mixture of krypton and xenon is much cheaper, so that's why we are using such a mixture. But however, there is some pedestal of longer radiation, and energetically it is about 50% of the whole spectra. And this is distribution in the focal spot. So there you can see 70, but we obtained higher than 100 millijoule per square centimeter, and the size, the diameter is about one millimeter in the focus. We have also in our lab different diagnostic instruments to study this surface after radiations, scanning electron microscope, focus ion beam with scanning electron microscope. We have also access to XPS, AFM, Raman, FTIR. So all the stuff that is required for characterization of the surfaces we have. Now I would like to show you just some examples of polymers that were irradiated EUV radiation. So these are typical polymer foil, 50 micrometer thick, which was irradiated 2 minutes. And after 2 minutes irradiated, we produce such a hole. So when you compare this information earlier that 1 hour was required for synchrotron to produce a hole 40 micrometer, so you see that it's not 2 minutes. So this results was quite promising for 10 Hertz operation rate. And around this central area for low fluxes, we observed characteristic cones, microstructures, nanostructures, and actually there are a few hypotheses. What is the reason of? In the book of Professor Bauerle, there are 3 of different hypotheses. What is the reason of this cone formation? Probably it is because of shielding of EUV light by impurities which are existing in a polymer. These conical structures can be changed by proper arrangement of the irradiation, by changing the flux, and also it depends on material. And these structures, these conical structures, and in the micro and nano scale, can be produced with different methods. Actually, in the world there are more than 100 groups, research groups, working on modification polymer surfaces with lasers, with lamps, with plasma sources, whatever. And the main task, it is bioengineering. However, it is also used for in photovoltaics and in LED, for instance, improvement of efficiency of LED. But we concentrate on biomedical engineering because we met colleagues from this institute in Linz. There is a group headed at that time, the head of this group was Professor Bauerle, and this group now, the leader of this group is Professor Johannes Heinz. So they study, they modify the polymer surface for more than 15 years for biomedical engineering. And they are using different lasers, excimer lasers, different wavelengths, plasma sources. And they found that during the modification of the surface, because of the UV light is penetrating inside material, so it causes degradation of the material, the bulk material. And they came to conclusion that when we use EUV light, which penetration depth is much smaller, so it will be able to modify the surface, but without degradation of the bulk material. And they proposal, because we didn't know about it, it was out from our specialty. So Johannes Heinz, he came to us and made a seminar and proposed to use the source for this application, and it was done. Now this is an example for PMMA, for 1 minute exposure time, for 2 minutes exposition, and you can see different structure depending on the flux. Okay, so I asked you that you, after half an hour exposition, half a minute exposition, you don't see any effect.
You focus your radiation, and we go far away in order to have coherence. So we have.
No, but
it is better to compare in this milliliters per centimeter square.
Okay, so this is. I would say that that the flux is less than 10 millijoule per square centimeter, but it is Yes. So the number of shots is quite different. Yeah. So this is issue.
Must be a time issue.
This is issue. I will be talking about. And this is another polyvinyl fluoride. We have used any type of polymers, and actually we made more than 4,000 such pictures. So the problem is how to analyze this picture, because we are not specialists on polymer science. We are not specialists on polymer engineering. So this is actually a task not for us. This is a real task for specialists from another area. But you can see that the characteristic feature that smaller exposition, smaller feature size. Right? So larger exposition, these features are larger. This is a polystyrene for 1 minute and for 2.5 seconds. Just for 25 shots, we have such a nanostructure. This is again 10-second exposition for PET, but this is very common material used in biomedical engineering, and also that ability to produce such a directed structure is quite important for cell cultivation, because in this case we can control even you can steer the cultivation of the cells. And finally, this EUV radiated polymers were used by our partner in Austria for cultivation of some biomedical cells. It was done by Bette Reisingen. Now he is doing a PhD on this topic, but using different lasers, not EUV. Anyway, she cultivated this Chinese hamster over whatever it means cells, and he found that good alignment of this. She observed a good alignment of the cells along the direction of walls. And what is important for me that after very short study, she discovered that chemical surface modification is more pronounced for EUV radiation than for laser irradiation. So this is important, that the group which was using lasers and different methods for many years, after a very short experiment, they found that EUV is more pronounced. Okay? So this is very promising results. This is an example of a surface roughening of Teflon. Teflon is quite not so easy for processing, but you see that using EUV we can easily obtain, after short exposition, we can obtain such strange, very nice features and structures. This is nano roughness on PET for different exposition. Look, this is only for one pulse. We obtain such nanostructures. There are also some self-organized nanostructures obtained by. Everything was obtained by Andrzej Bartnik and co-workers. So this was their study. This is an example of this worm-like structures, which can be observed also using traditional technique with lasers and plasmas. As I showed, we have XPS to study the contamination and chemical composition of the surface, and we found that after UV radiation, the composition of oxygen and carbon can be changed. So it is a way to control this, and it is also very important for the biocompatibility control. So you can see that after radiation, the carbon concentration of carbon is increased, and opposite the concentration of oxygen is decreasing. Interesting new phenomenon was that we observe so-called nanocavities. They are formed. They are visible on the surface of the irradiated polymer in a form such as bubbles. But when we go inside of material, so we see that these bubbles also are existing inside of material. So this is a question: what is the mechanism of formation of this nanobubbles? This is another image of this nanobubbles. And maybe this is a hypothesis, however, because as I said, it's new that these nanobubbles are formed because of nano explosions induced by EUV photons. You know that it was observed that such a micro explosion in crystals can be induced by the very low energy of laser energy, which is focused inside material. Low, it means less than 1 nanojoule. And it was observed by a few groups, and they made some calculation. In our case, we found that when we are able to absorb energy on the level of few hundred EV, it means that if you are able to absorb a few EUV photons in the same place, in the same time, so we are able to create such a void, such a cavity. So it's something like similar to multi-photon ionization. So we have a multi-photon nano explosion in this material. However, we discussed about it with some people working in this area, so it is more or less questionable. However, I think that it can start the ablation process, because a single photon can break a single chain of polymer. Okay? But to produce a void, to produce such a nano bubble, we have to have more energy. And if we have one energetic photons, okay, so it will be not absorbed in this specific area. So we have to have few of them. From these simulations made by Professor Jach in our institute, we estimated that this energy which is required to produce such a void, such a nanobubbles, on the level of few hundred, 500-600 EV. So it means that few EUV photons can produce such such nanoparticles. Finally, under this project, together with Johannes Heinz and our colleague from Lithuania and from the Czech Republic, we built such a source which is dedicated for processing polymers. We found that people from outside of our community, I mean laser plasma and laser, they are even afraid of our experimental arrangement. I saw that when some chemist visited our laboratory, so she didn't like our stuff. So that's why we wanted to build an instrument which will look similar to scanning electron microscope, which is quite common in a new laboratory. So we built in the form of a column, and in the upper part of the column we have a source, then below there is optics, and here we have with the easy access we have a chamber in which chemists or biologists can put the sample, and under control of the computer can make some irradiation experiment. Laser is hidden, there is no laser, laser is below, so everything. So it looks like this. Here you can see for the first time EUV beam. This is EUV beam. It can look blue or red, so this is visible light. Okay, so it was of course made by putting some residual gas into the chamber. This source was used by in further investigation. This is example of research done by our student and now our colleague in our group, Łukasz Wężyński. So he had no any experience with this stuff, and after very short training, he was able to manage and to operate and to make processing, and he was able to obtain new results that can be used for Prismaster. Besides processing and modification of polymers, we also try to use this technique for microstructuring, to produce some parts. And we found that this EUV light is quite useful. For instance, there are some polymers that are chemically resistant and quite difficult. It is quite difficult to process them using lasers and X-ray micromachining with synchrotron. But we found it's quite easy to process these polymers with EUV photons. Right? So this is another example that we can find some sort of materials that are important for some engineering application that can be processed easily with EUV photons. Also, we performed some preliminary studies on EUV processing of non-organic materials. I would like to point out your attention. We observed surface melting after irradiation of EUV light. And maybe someone you notice a paper in Nature when the melting of the surface with EUV photons from the flash was observed for the first time 2 years ago. It was published in Nature, but our result is not of course to be published in Nature. But anyway, you see that with quite low fluency, low flux of EUV photons, we are able to melt the surface. So I think that is another topic. Maybe it would be reasonable to propose such a PhD project because there is a lot of interest in the semiconductor industry to study, because they are using different ion beams, electron beams. They are using different techniques to change the surface of semiconductors, of metals, and I think that EUV light could be applicable because of this energy. Yeah, we have to go to this community, not to close to our. Okay, this system is also equipped with additional valve, so we can use, it is called reactive processing. Okay, so we can use additional gas in this focal region, And this gas can change the wavelengths, can change the spectral range, but also we can produce some active medium, for instance, oxygen, active oxygen or active nitrogen. This is an example of irradiation of such a stream of gas, injection in the focus. This is for helium. We are able to produce such a nice picture of ionizing gases. We measure the spectra of these gases. This is a spectra for neon, for helium, with some interesting feature. Actually, we proposed this topic. I mean, photonization of gases with EUV photons, because it is completely new topic. There is no results on this study because not availability of the source. So also this is another proposal for the next topic: the photonization of molecular gases. And these are example of irradiated PMMA with additional gas. So you can see that when you use a nitrogen, there is some possible chemical reaction, some reactive processing. When we use a noble gas, there is no chemical resistance. So it is another way to improve the process of UV processing. This is another interesting result. We observed that after EUV radiation with nitrogen, then we observed some traces of micro and nanoparticles which ablated from the surface. So it was another new phenomenon. And there are some spectra obtained for irradiated polymers. This device is also equipped with mass spectrometer, so this mass spectrometer can be used for to study the investigation on interaction of EUV interaction with different polymers. We can measure the spectra, mass spectra of irradiated polymers. So this source was, I would say, mentioned when I had a talk at the SPI Photonic West conference, and then I was invited to write a short article in the SPI newsrooms. Then when this Eureka project was finished, so I had a phone call from Brussels, and they proposed us to choose this project as a Eureka success story. And last month, even in the Polish version of Scientific American, there was a short article about the source and the new technology. So there was something, I would say, there was some note that we have done this. So finally, I would like to say that in our disposal is a very well equipped laboratory for micro and nano processing of EUV using EUV photons, and it can be used for processing polymers, for modification of polymer surface, for micro and nano publication, and I'm happy that we will have the first external user in it. However, in our group there is a young lady, scientist, Basia Korczyk. She is a chemist, so she will work together with Inam on this topic. And also, I'm very happy that Dermot Brabazon, he will support us as a real specialist on biomedical engineering. Okay, so now I would like to skip to another application of our source, EUV imaging in nanoscale. So the motivation, the basic motivation was actinic inspection of EUV lithography mask. But because I'm rather skeptical on EUV lithography, so finally we also found different areas that this type of microscope or nanoscope can be used. Anyway, this is a schematic of this. So this is our source. This is an ellipsoidal corrector we are using such a multi-layer ellipsoidal mirror to collect and also to select radiation in band. Because as an objective, we are using Fresnel plate, and from the lecture of David, you know that Fresnel plate required monochromaticity. And we are using commercially available Fresnel zone plate with these parameters, 50 nanometer width of the outer zone. So we would expect a resolution about 60 nanometer. And so this is a ellipsoidal mirror, which is a crucial part of this system. The mirror was developed in collaboration with Reflex at the time, now Rigaku company in Prague. They supplied the substrate, and the coating was made by colleagues from Jena. And we are using argon gas path target, and in the argon plasma there are several lines, and one line is exactly at 13.8. And using this multi-layer mirror, we select the single line. So we have a quasi-monochromatic emission in practically one line. There are two lines, but they are almost together. So it is quasi-monochromatic line, which is acceptable for this imaging with using Fresnel plane. The source was characterized carefully by Przemek, so these results are published in this article. And the schematic of this microscope is here. So you see that a very small optical table, half meter, 1 meter, very small, very compact. So it's not a tabletop, but we call it a desktop device. And this is source, chamber with a collector and microscope. And Przemek made some investigation, and he got images, and he used as a test object, he used such a grating which are micro holes, 1.5 micrometer in diameter, and this is an EUV image of this structure. And from the night edge test, he got a resolution on about 50 nanometers. So which is a quite good result. Better resolution was obtained at synchrotron or large laser facilities, right? So for such a tabletop, I think it's a record. Now Przemek is going further. He's using this EUV to study, for instance, nanostructure like nanowires from different materials, some structures inside. Unfortunately, he didn't send me data, and I have no in this computer, so I am not able to show them. Now he's moving to shorter wavelengths, to water window. And so he prepares such a new setup, new arrangement, which is equipped with a soft X-ray condenser to condense grazing incidence in this case, because we have no access to multi-layer optics on this water window range. So we are using axisymmetrical grazing incidence as a condenser, again made by Rigaku company. And this is a setup for using Volter type 1 axisymmetrical mirror. We have such a system, and he obtained recently images using in the setup. But now he is preparing imaging system with Fresnel zone plate for water window. So I think that it could be also. It was suggested and proposed as a project in this second cohort for EXTATIC. Imaging, nano-imaging, imaging nanoscale using EUV and soft X-rays. Another application of the source is EUV pulse radiography. So the purpose, the reason of this is the need of characterization of the gas path target, I already mentioned. And so we have prepared such a system. This is our source, EUV beam. We select from spectra of xenon. We select emission in band using polysilicon mirror, and this quasi-monochromatic EUV beam is used to irradiate, to backlight the gas path target under study. And this is experimental setup, chamber source. This is one of target we have developed for laser metal interaction experiment. It is elongated up to 15 millimeter long gas path target. So you see again that this is not really remind a jet, rather like an elongated ball. And recently, because there is some interest to use multi-jet gas path target for high harmonics generation, it's demonstrated by in this experiment in Nature in Germany, in Italy, and Valer Tosha, he made a very nice simulation, and they presented that such a multi-jet system can improve our high harmonic generation. So we made this because we found that sometimes in this experiment, this arrangement was very, very, I would say, not well done. Pretty, just some tube with hole. So we made this more, I would say, professional way. So this is our arrangement. And there are examples of this characterization results. So you can see different EUV shadowgrams of the multi-jet produced with 5, 7, 9 holes. And from after processing of this image, we can evaluate. We can obtain the profiles, dentate profiles. So we can see that we have separated profiles, but very close to the nozzle block. But some in these papers I already mentioned, they put focus at 1 millimeter, 1.5 millimeter. So if you are not lucky, you can have a case there is absolutely no modulation. So this is very risky. You know? Okay, and in our laboratory we have a high-intensity laser system that was dedicated for high harmonic generation, and we suppose that we will be able to use our gas path target for high harmonic generation. Unfortunately, the system all the time is broken, and I really don't know what will be in the future. So we performed this experiment in Prague in collaboration with our colleague, with Misha Kozlova from PALS. So the arrangement was after Bill talk is here for you, that we put in the focus of the laser system, we put our gas path target. Here you can see traces. These are plasmas created because of the direction of the laser beam with the separate jets. And there are spectrum obtained from of harmonics from the gas cell, and for comparison with the multi-jet gas target. There are some differences now because it was obtained 3 weeks ago, so now they are discussing with Misha Kozlova how to explain this, what is going on, and it is reasonable or not. We also develop a dual gas multi-jet gas path target because there is another very nice paper. It's a group, MAT-CEP. They made a very nice experiment. They use such a device, and we have developed our device and make characterization experiments. So you see that now we are able to produce very well separated stream of different gas with very, very good modulation of density. So now the system is waiting, Bill, for joint experiments. Okay, so we also use this target for generation of active media for X-ray laser. So there is some proposals by Milchberg and by Russian colleagues to produce such an active media in a form of the waveguide, plasma waveguide. And they are using Axicon, which is used and focus laser beam in the gas filling the chamber. And we propose to use, instead of this gas filling the chamber, we propose an elongated gas path target. And we perform such preliminary study in our laboratory. We could produce such an elongated channel. And we had collaboration with colleagues from Berlin. Even it was published in some journal, and I don't know German, but it means that Poland pushes research on X-ray lasers. And there are students from our institute, they went during vacation for training, for 1 month training to Berlin.
If you push a gas laser in a car.
Yes. Okay. So we have another, as I said, high energy laser laboratory, which is equipped with the neodymium YAG laser system with such a parameters, 10 joules, 10 nanosecond, 10 hertz. So we would like to establish such laboratory beamline of EUV and X-ray generation. So we expect that on the output we will have parameters comparable to the very, very small synchrotron, maybe first generation. We will see. And also for laser metal interaction studies to producing these waveguides or shock waves in solid material. So the system was installed and it was used in preliminary experiment. And the experiment of the soft X-ray laser active medium, it is like this, and we already started study. So it would be again additional proposal for very good project related to soft X-ray and EUV technologies. So our laser metal interaction group is presented here. 10 people, including Ahad, and 3 of them are Tomasz Fock and Łukasz. They already studied. I mean, they are PhD students at the Faculty of New Technologies, but they work with us on the project. And we offer, some of you already mentioned that we offer a short-term training visit, which were organized both under Laser Lab Europe and this cost action. So we offer a scientific program, accommodation and meals. And there is description of this program, and this call is open for any time. So we can arrange such a visit, which in a term which is convenient both for us, but also for applicant. And this is a web page of our group, so you can find information about this training here and contact with us. So I finish. Thank you very much for your attention.
Questions, anyone?
Yes, go back to that commercial system of X-Play. What are the parameters of the laser that sits under?
Yes, good. The big one or small one? Small one. We have different. We have half joule, 4 nanosecond, 10 hertz. We have 0.8 joule, 4 nanosecond. There is also option 1.6, 40,000 euro joule. So and it's a very compact, and actually we found this laser as a very good compromise between price, maintenance, and easy to operation. And this setup, vacuum setup, is made by Prevac company. So this is another partner. We have such as 3 strategic partners: Prevac, Expla, and Rigaku. Because to have such a source, we have this. Without them, no source.
Many years ago, Active Research Corporation tried to take the area plasma continuum silent target, turn it into a commercial product. But I think the problem was that they agreed.
Yes, this is a serious problem. I think that even the EUV high average power source will be available, though still the problem of the breeze will close this problem because of degradation of mirrors.
They are
yeah, but they are talking about, you know, the curtain, gas curtain, something. They just put, you know, these people, they say nothing, I would say, which is I don't understand how they want to solve this. They address this, but without any real even proposal.
I do not know how it is with laser sources, but with EHR sources they do have, and they measure, and they show, and they invest a lot of time, and the whole group only dealing with these deep issues. And they have, I think, also part of the solutions which are very nice. It's not only glass. It does not work with only glass.
No, they propose to use some magnetic fields and the combination of electromagnetic fields, but now there is a question of ions. Ions will also degrade strongly.